Hello guys, welcome to Ramtel Solutions. Today we will be looking at work, where we will be defining what is work and maybe do some calculations as well. Do some calculations as well. And we will also define positive work, negative work, and also show you what we mean by zero work being done. Okay, so we talking work and we're going to differentiate it between the normal everyday usage of I'm going to work, I've got homeworks, and I've been working in my yard. Okay, we're going to differentiate that. So we're going to define work in terms of that definition by energy. That said, energy is the ability to do work. We want to define what is this work. Okay, so without any waste of time, let's talk about it. So we're talking work. So we're saying work is done. Okay, we're saying that work is done when a constant force acts on a body or an object while it undergoes displacement. Okay, so work is done when a constant force, acts on an object while it undergoes displacement. Okay, or you can say, you can basically say work is, or rather work done is energy transferred from one object is the energy transferred from one object to another. Okay, it's energy transferred from one object to another. From one object to another. Right? To another. So, this is the work definitions that you will use. It's up to you which one you like. However, I like the first one, which says work is done when a constant force acts on an object when it undergoes displacement. One of the reasons I like it is because it underlines force and displacement. By the way, work is delta, it's W, sorry. Work is W, right? So, as you can see, this is a product of two vectors. So we should basically be saying work is a vector quantity. And in addition, it is measured in joules. Okay? It is measured in joules. Okay? It is measured in joules, which we call capital J or symbolizes capital J. Okay? Right. So let's talk the formula that we use. Okay, so the formula that we use is that work is equal to F delta X cos theta. Okay, it's F delta X cos theta, where this W is work done, right? This W is work done measured in joules, while this force here, this F, is the force acting on the object, right? This is the force acting on the object. Obviously, force is measured in newtons. Yes, it's measured in newtons. This here represents the displacement, right? This here measured the displacement, which is measured in meters. And the theta, angle theta, this is the angle between the force and the displacement. Okay, angle between the force and the displacement. Okay? Angle between the force and the displacement. Right. So this is the equation of your work done. This is how you calculate your work done. Work done is equal to force times displacement times cos the angle between the force and the displacement. Okay. Let me give you an example. Example. Calculate work done when given this diagram here. So let's say our force is 50 newtons and the displacement is, I will say 3 meters. Okay? So we know when we calculate work, we say work is equal to F delta X cos theta. Remember what we had said, cos theta is the angle between the force and the displacement. The question you should ask yourself is, where is the displacement going to? To the right. In which direction is the displacement? It is to the right. When you look at the object, in which direction is it heading to? It's to the right. The force is also heading to the right. So both the force and the displacement are in the same direction. So our theta will be 0 degrees, right? Our theta will be 0 degrees. Therefore, our answer is the force is 50 and the displacement is 3. The angle is 0 degrees. On your calculator, this returns positive 150 joules, right? It represents positive 150 joules. So this means this is the energy it takes to move the object, right? This is the energy it takes to move the object. Okay? All right, perfect. So this is the energy it takes to move the object. All right. Moving on. Now, let's now look at positive work. Okay? We will now look at positive work. Okay, we will look at positive work. I will leave a space here so that we can say something about it later. So let's consider a force moving in the same direction as the displacement. Again, I will take the example in the previous page, 3 meters, and the force is 50 newtons, right? So you agree with me that in the last example, we said the angle here is 0 degrees, all right? Because the angle that's doing work on the object is in the same direction as the displacement. So this is 0 degrees. So generally, we can say W equals F delta X cos theta. So generally, we will say cos 0, right? Now, okay, so cos 0, we know it to be positive 1. So this means we have positive delta X. Now, when we substitute these values, we basically got positive 150 joules, right? We basically got 150 joules. So when positive work is done, the force is moving in the same direction as the displacement. All right? Again, when positive work is done, we're saying energy is being transferred, right? Energy is being transferred to the object. This will be long. So let me just say energy is transferred to the object. Okay? Energy is transferred to the object. Okay? Energy is transferred to the object. Right? So when positive work is done, energy is transferred to the object. Remember, for positive work to be done, the force must act in the same direction as the displacement. All right. Now, let's look at another point. I'm going now to look at negative work. Okay, I'm now going to look at negative work. Now, here we consider displacement and the force. Maybe let me say force is friction. I'm going to say it's 13 newtons. I'm going to say my displacement is still 3 meters. Okay, so as you can see here, the force is acting in the opposite direction to the displacement. So if it's acting in the opposite direction to the displacement, maybe we can say this is 180 degrees, right? Maybe we can say this is 180 degrees. Okay, this is 180 degrees. It's not a maybe, it's a fact. This is 180 degrees because if this is your object, here's your force and here's your displacement. This is 180 degrees. Okay, perfect. So now, when we generalize this, we will say W equals F delta X cos theta. F delta X cos, what is our theta? 180 degrees. Now, we know cos 180 degrees is minus 1. So, this means we have negative delta X. Okay? We have negative delta X. Now, let's look at it using this example. Work equals F delta X cos theta. What is the force? It's 13 newtons. The displacement is 3. The angle, it's 180 degrees. Put this on your calculator and tell us what you find. Your answer is negative 39 joules. Right? Negative 39 joules, isn't it? Good. Now, when negative work is done, energy is removed from an object. Okay? Energy is removed from an object. Right? Energy is removed from an object. So, for negative work to be done, the force must act in the opposite direction to the displacement. Okay? The force must act in the opposite direction to the displacement. Okay? Perfect. Now, let's look at zero work. Let's look at zero work. Now, zero work, I'm not going to leave a space. Let me just do this. Let's say the force here is, I'm going to say 16 newtons. And the displacement, I'm still going to say it's moving to the right for 3 meters, or by 3 meters, right? Now, I want you to look at this diagram. When you look at this diagram, the angle between the force and the displacement is basically 90 degrees, right? As you can see, the force is perpendicular to the, rather the direction of the force is perpendicular to the direction of the displacement. So this is 90 degrees, right? Now, let's generalize this. Work equals F delta X cos theta. So F delta X cos 90 degrees. This is F delta X. What is cos 90? Cos 90 degrees, all know it's 0. So therefore, this means 0 joules. So when a force is acting perpendicular to the displacement, there's 0 work done. Okay? There is 0 work done. Now, let's look at this example. Work equals F delta X cos theta. The force is 16 newtons. The displacement is 3 meters. The angle is 90 degrees. Your calculator will return 0. So this is 0 joules. Okay? This is 0 joules. So I repeat, when a force is applied perpendicular to the displacement, I repeat, when a force is applied perpendicular to the displacement, there is zero work done to move the object. Okay, so now you have it. All right. So let's now try should we try a summary example? No, not as yet. Okay, time is still on our side. Not as yet. Let's try to summarize something. For work to be done, the force must act parallel to the displacement. When I say parallel, it can be in the same direction or in the opposite direction. Okay? For work to be done, the force must act parallel to the displacement. Okay. Let me write it down maybe. For work to be done, alright, for work to be done, the force must act parallel, right, must act parallel to the displacement. Remember, when I say parallel, I mean it could be same direction or opposite direction, right? Or opposite direction, right? It could be same direction or opposite direction. So remember, when you do your calculations, check which force is doing any work. If the force is perpendicular, it will not do any work. If it's parallel, check whether it's in the same direction or it's in the opposite direction. If it's in the opposite direction, it will be positive work. If it's in the opposite direction, it will be negative work. I repeat, for same direction, it will be positive work. For opposite direction to the displacement, it will be negative work. Now let's try a summary example, which I want to make it a bit difficult, but it's okay, it's not going to be that bad. So, summary example, I'm calling it summary example because it's the last example for this video. So, I will say calculate the work done on the object. Calculate the work done on the object. Okay, calculate the work done on the object. So here is our object, and then here is the force. So let's say this force here is 60 newtons and it's acting at 15 degrees. The displacement, I'm going to say this time it's 2 meters. Okay? This force on its own, we can see that we can resolve it into its horizontal and vertical components, right? We can resolve it into its horizontal and vertical components. What I mean is it's like this, it's acting at an angle. So we can resolve it into this. So here is it. It's 60 newtons, right? This will be its horizontal component, while this will be its vertical component, while this will be its horizontal component. Remember, it was acting 15 degrees from the x-axis or from the horizontal axis, right? So when you look at this, this is a resultant. Can you see that? It's a resultant force. Remember, it has the same magnitude as the sum of these, right? So when you have resolved this, you can see that now you have a horizontal force and a vertical force. Which one can do work on the object? As you can see, F sub y will not do work on the object. Why? Why will it not do any work? Because as you can see, the displacement is to the right, while F sub y, it's going upwards. So that is perpendicular to the displacement. So it's zero work done. But F sub x will give us the results. As you can see, F sub x is adjacent to 15 degrees. So we can use cos 15 degrees equals F sub x over F, which is F sub x equals F cos 15 degrees. That is 60 cos 15 degrees. Right? So let's now calculate the work done. So the work done is F delta X cos theta. This F here represents work done by the horizontal force, all right? Which is, do not confuse it with the F given here, okay? So this is simply to say the force that is acting on the object. So the force that is acting on the object that can allow us to perform any work is F sub X. What is it? It is, I think it was 60 cos 15 degrees multiplied by the displacement was 2 meters times cos the angle that's doing work on the object and the displacement. That angle is F sub X. F sub X is acting in the same direction as the displacement, so the angle will be 0. Right? Now let's get this. This is 120 times cos 15 degrees. So our answer is, I know cos 0 degrees is 1, okay? So this is 115, correct to 2 decimal places. It'll be 115,91 joules. This is positive work, right? This is positive work done. So energy has been transferred to the object in order for it to move. Can you guys see that? So this is it, guys. This is your introduction to work, and the next time I see you, it'll be when we talk network. Please don't talk your cellular networks. If we're talking physics, of course, cellular networks are also an application of physics, right? They are, but we're talking motion now. So when I see you next time, it's network. So see you next time, and bye.